Welcome to Flink Forward Asia 2024.
Next, we have a trio speakers for the next presentation on Apache Flink 2.0, streaming into the future. The first one, we have Mr. Xintong Song as Alibaba Cloud Software Engineer Staff, Apache Flink PMC member, and Apache Flink 2.0 Release Manager, and together with Mrs. Yuan Mei as Director of Engineering Alibaba Cloud, Apache Flink PMC member, and all together with Mr. Lincoln Lee as Staff Software Engineering, Alibaba Cloud, Apache Flink PMC member. They will talk about the Apache Flink 2.0. Please, for the first one, please welcome Mr. Xintong Song.
Hello, good morning, everyone. My name is Xintong. I'm from the Alibaba Cloud Flink team, and I'm one of the Flink PMC member, and also I'm the release manager of the Flink 2.0. And today is my honor here to share with you about the Flink 2.0, together with my colleagues, Yuan Mei and Lincoln Lee, who both are the PMC members. Well, we have mentioned that the Apache Flink has joined the Apache Software Foundation in 2014, but the first formal version, the Flink 1.0 version, was actually released on 2016. And after that, the Flink has released many minor releases, and by minor releases, I mean like the 1.x releases like 1.17, 1.18, but we never released another major version. Well, in the past 8 years. And last year, we realized that as the Flink has been involved, a lot difference from when it was shaped as Flink 1.0, and we are facing more and more challenges. So to address these challenges, we need to make some significant architectural upgrade to the project. So we kicked off the planning for the Flink 2.0 in the community in last year, April. And the preparation of the Flink 2.0 takes quite long. We have been through 3 minor releases, the 1.18, 1.19, and 1.20. And finally, in this October in Berlin, Flink Forward Berlin, we just announced a preview release for the Flink 2.0 version. And the formal Flink 2.0 release is expected to be shipped in early next year. So we can see that the preparation for Flink 2.0 takes really long. It's almost 2 years from the from April last year to early next year. So the reason it takes this long is because we are making some compatibility breaking changes in this major version up. And we want to leave enough time for our users and for our partner projects to adapt to these breaking changes. So here is a summary of the breaking changes. We have removed some deprecated APIs, for example, the dataset API, the Scala datastream API, and some old connector APIs. And for the existing APIs, we also made some updates, like the datastream API and table API, and of course REST API, the Flink client and SQL client. And for the configuration, we have removed the old flinkconf.yaml file, and users can now use the new config.yaml file, which is strictly following the YAML standard. And we also removed some deprecated config options. And for the state, it needs to be noticed that the save point and checkpoint compatibility is not 100% guaranteed between the 1.x versions and the 2.0 version. Well, this is mostly because of we did some upgrading to the serialization framework of Flink. And the community is working on some tools to help our users to migrate between the incompatible states. And other things like we have dropped the support for Java 8, and the per job deployment mode will be removed in the 2.0 version. Well, we just mentioned that we are removing some old connector APIs. That means if there's some existing connectors which are using the old APIs, they need to be migrated to the new APIs before, in order to work with the Flink 2.0 version. So as a first step, the Flink community will work on the following 4 most commonly used connectors: the Kafka connector, Pymon connector, JDBC, and Elasticsearch. So this will be supported by the time that Flink 2.0 formal release is out. And for the remaining connectors will be supported gradually. And the community developers are more than welcome to join us in accelerating the adoption of Flink 2.0 for the community, for the connector ecosystem. Okay, so we have spent a little time on the progress and the breaking changes of Flink 2.0. And the remaining time of this talk will be focused on the technical highlights of Flink 2.0. And we are going to talk about 4 directions: the streaming, the stream batch unification, the streaming lakehouse, and the AI topic. So firstly, we want to talk about streaming. And for this part, I'd like to invite my colleague, the Flink PMC member Yuan Mei, onto the stage. So please, Yuan Mei.
Thanks, Xintong. So, hello everyone. My name is Yuan, and I'm from Alibaba. I'm the Director of Engineering at Alibaba Cloud. And I'm also a PMC member of Flink. So, today I'm going to share some of the very exciting work that we've done in Apache Flink 2.0, and which is the disaggregated state management. Disaggregated state management enables Flink's cloud-native future. Let's start and how it works. So, this year is the 10th anniversary of Flink, after it becomes the top-level project of the Apache Software Foundation. Well, over the past decade, you know, like Flink has been blooming. I mean, like, it's been widely used in many different areas, and it's developed rich upstream and downstream ecosystems. Well, ecosystems. So, Flink has become a de facto standard for stream processing in open source area, in academia, and in industry globally. Well, at its core, I think these 3 symbolic characteristics are still at its core of the Flink's characteristics, which is distributed in large scale, high performance, and stateful computation. What is stateful computation? For a stream processing system, the input is unbounded and continuous, generating the low latency output based on this continuous input. And the stateful computation basically means that basically means that's an intermediate result of this stream processing. So for each input record, it has to access the storage, the intermediate results, and then generate the new output. Hence, state access latency is critical to performance. Well, remember, this is pretty important, and I will mention later why it is so important. Because of the state latency is critical, so in Flink, we co-locate the state store and the computation together, as shown in the middle graph. So state is snapshotted, has to be snapshot periodically, so that when we have a failure or we have to do the rescaling, we have to reload the state or redistribute the state. For systems like for distributed system, we have to make sure the snapshot is consistent. By a consistent snapshot, it actually means for each distributed node, it holds the subpart of the snapshot. Those subpart of the snapshot has to correspond to exactly the same input offset. So the procedure to make the consistent snapshots actually is a very well-known and famous Flink checkpoint procedure. Well, this tightly coupled architecture guarantees the high performance for Flink, but it to some extent hinders the expansion and the development of Flink, especially when the state size grows large, which exceeding the capacity of the local disk. And together with the cloud native trending in the recent years, we actually have more challenges. If you could see, we summarize the challenges in these 4 parts. The first is computation and storage scale independently. Well, this is easy to understand, right? Because we do not want to pay extra money for computation simply because my state size grows large. And the second is containerization. Well, containerization is a commonly used technology in cloud native, and it requires predictable, smooth resource usage. So why it is a challenge? Because as I mentioned before, in the tightly coupled architecture, the checkpointing procedure is happening in a very short period of time, which boosting the resource usage in CPU, I/O, or network, which actually have a resource usage peak, make the entire cluster unstable. So this is a challenge in the containerization technology widely used area. And the third part is now the cloud storage like S3 OSS is commonly used and available. So how we can make use of such cheap and massive storages? They are highly available and scalable. And how can we make use of them? With the improvement of the hardware or network speed and bandwidth improvement, is it possible that we get rid of the local disk? Well, the last challenge is elasticity for stateful computing. We know that for stateless computation, rescaling is very fast and cheap. But for stateful computation, we have to redistribute the state across the stateful containers when we're doing the rescaling. So how we can accelerate the state redistribution, even if we could achieve the redistribution within sub-second, that's also a challenge for us. Well, this is our solution. That's exactly what we do for in Apache Flink 2.0 in the disaggregated state management. And this is our solution, ForceDB. ForceDB, forced stands for for streaming. And ForceDB is the for streaming DB. And it's a very simple and straightforward name with the very good willingness. ForceDB, I remember that. It's already open sourced. And we wrote it. So what is ForceDB? ForceDB natively supports writing to and reading from DFS. DFS is the distributed file system, like S3 and OSS, or simply HDFS. So how it magically just solve all these problems? Let's see it one by one. So first, state is no longer constrained by local disk, because now we can writing to and reading from DFS directly. And DFS, in theory, it could have like unlimited storage space, and not constrained by local disk anymore. Well, the second one is instant rescale and recovery is also possible right now, because now we can read from the DFS directly, so that we do not have to download the state when we're doing the recovery or rescaling. So the downloading time is saved. And the third is, well, now we actually have the working state and the checkpoint data writing to the DFS altogether. So underlying, they can share the same physical files. In that sense, we can make the checkpointing procedure lightweighted. Well, since I have already mentioned, the checkpointing procedure is actually generate the resource peak usage in the current tightly coupling architecture. So if we can make lightweighted checkpointing procedure, then it could smooth the resource consumption in a large way. Well, architecturally, you can see it's from the left-hand side of the graph to the right-hand side of the graph. Seems like it's just a very simple change, right? Just to replace the local disk to a DFS. And is that simple? Is that so simple? Oh, of course not, right? So then if it's that simple, it won't take 10 years. So why it is not that simple? The key fact here is, as I mentioned at the beginning of this talk, because the state access latency plays a critical factor for performance. And when we are accessing to the DFS, comparing access to the local disk, the latency is 10x time longer, which indicates that we will get 10x time performance drop, which is not acceptable. Now, if you just simply replace the local disk with DFS, you will get, what we will get is 10x performance drop, and the Flink is not usable anymore. But this is actually why the reason for so many years there are so many attempts to make the disaggregated storage, but there's no succeed. That's the reason. Well, the key insight here is the first one, the async execution, which is separating the CPU processing out from the state I/O access. This is very, very key insights how we can actually make the performance comparable to when we are accessing the DFS comparing to access the local disk. So the second point in the middle column I want to highlight is the checkpointing procedure. So for a streaming processing system, a native and a deep integration of database and the checkpointing procedure is have to be done. Otherwise, you cannot guarantee a consistent snapshot, and you cannot guarantee exactly once, and you lose all the benefits that Flink provides. And otherwise, if you do not have the deep integration, it has no difference that you are using an external database. So we made a lot of efforts in this part, and also achieve native elasticity support. When the third part is the cache. Well, we all know that when we're using disaggregated storage, then the performance, the cache is critical to boost the performance. So if the local disk is not a must-have, but if we do have local disk optionally, right? So we should make good use of it. So we also make a lot of efforts to develop the hybrid adaptive tiered cache. Well, I do not have time to go to all the details, so I have a more detailed talk on the upfront. So if you are interested, then you could go to the link and see the more detailed talk about how this fancy stuff happens. When Flink 2.0 is expected to be released early next year, and in the blue box there are 6 major areas we're going to achieve in disaggregation. And as I said before, forced DB and async execution are the founderstones that make disaggregation successful. And the forced DB preview version has already been released 2 months ago. The link is shown here, and it shares some of the experiment results. And if you are interested, you could also have some end-to-end experience and play with it. And the formal version would target for Flink 2.0. And they have the end-to-end support for Flink disaggregation, and they also have 70% SQL async OP support, and also support the SQL migration. Okay, so here are the list of flips, the Flink improvement proposals for the disaggregation. So if you are interested, and they are all public in the Apache Flink community, they cover all the details of the technology that I've covered today, just for your reference. And then last, I want to share some of the experiment results of the ForceDB preview version. And in short, these experiments are all comparing to the latest version of Apache Flink 1.20. So I want to have 3 highlights here. The first one, so in the synchronous execution mode, this aggregation is 10x slower as expected. Well, what does it mean? It means that if you just replace the local disk with a DFS or use any kind of external database, that's the performance you will get. You will get 10x slower performance. Well, that's too bad. And what do we do? So, as we said, we introduced the async execution mode. So in the async execution mode, let's see how it works. The performance of disaggregate without any cache. Cache here means local disk. So In the async execution mode, the performance of disaggregation without any cache is comparable to Flink 1.20. By comparable, I mean 15% slower. Well, it's still slower, but comparing to 10x slower, it's much, much better. Okay, then what's more? Let's see the third one. So in the async execution mode, the performance of disaggregation with 50% of cache improves 50% comparing to the Flink 1.20. So what does it mean? So that means with only half of the local disk, now we actually achieve 50% better performance than before. So that's amazing, right? So if you're interested in how this amazing things happens, just go to check the technical docs. Or if you're interested, I also had a talk that listed above. So that's covers all that I want to mention in the streaming part. So next, I probably want to invite my colleague Lincoln for stream batch unification.
Yeah, thanks Yuan for his great talk. I'm Lincoln, also come from Alibaba Cloud. Now, let's talk about the streaming batch unification. So what exactly is the stream batch unification? From a data engineering perspective, we can describe in one sentence. That is storing just one set of data and writing one piece of code to meet both real-time and offline data process needs. So one code also implies the requirements for the unification of execution engine, because even use SQL as the user API, we have still differences in different dialects. So the most straightforward way to achieve writing just one piece of code is to use one single engine. Now let's look at the real challenges in real-world data engineering architecture. On the left is the classic Lambda architecture. We can breaking down by layers. We have the data ingestion layer, which is responsible for the data into lakes or warehouses, and the data storage layer, and consisting of the offline storage and message queues. And the rest is the data development based on the specific computing engine. So from top to the bottom, we have two different tech stacks for the two pipelines. And this will lead several issues in development, such as high storage costs because of the storage redundancy and the complex tech stack. And for the users, they need to develop separately for both offline and real-time development. And this may cause potential data inconsistency. In recent years, the new unified stream batch lake storage, like systems like Paimon, often, they make the lakehouse architecture more useful. And the Paimon, like Apache Paimon, the systems supports both the streaming read-write and the batch read-write. Together with Flink engine, it can provide a continuously incremental update pipeline and make the pipeline greatly unifies the computation and the development. But there still remains some issue unresolved, such as when do data backfilling, the stream mode will be very slow. And if we want to use the batch mode refresh with better performance, then we still need to modify this original circuit. Then let's turn back to the perspective of Flink. Over the past decade, from the engine architecture of streaming batch unification to the production-ready circuit engine, we have achieved computational unification. The new Apache Pymon, it realized storage unification for streaming and batch. And Flink CDC provides a unified ingestion. So to implement a full-stack streaming batch development stack, what is still missing? Yeah, the core issue to preventing the unification of stream and the batch code lies in the difference in different different programming models. Yeah, let's say the batch model, the batch processing is designed for the static data, typically involves the partition operation, such as insert override partitions, and each partition has defined filtering conditions. But streaming processing, on the other hand, it will deal with the streaming data, the unbounded data. It will not involve such partition operations, so it will be different with the batch circle. So to address these issues, we have introduced the new materialized table. Here is, on the center, we have a simple script to create a materialized table. It consists of three main parts. You have the first is the create materialized table object. Then a Pymon table will be created under the Pymon catalog. The second is the data freshness. Users can set the desired data freshness as they need. The last part is the query definition, which describes the business logic. So with materialized table, users can use the declarative circle and have a unified one. And the users just need to describe their business logic and set the data freshness as they need, and the rest part, the engine will handle the rest part automatically. So users when use materialized table, they can improve their maintenance work in addition to writing one piece of code. For example, during a promotion, we provide users with the second level real-time data. And after the promotion ends, in order to reduce operational costs, we can just change the data freshness to day level with a single click. And for the data backfilling, which is commonly used in data warehouse, and we can also trigger it with a single command. Yeah. Materialized table not only helps users to achieve writing just one piece of code, improving their development and maintenance efficiency, but also bring cost efficiency. Yeah. Materialized table supports three different refresh modes. The streaming mode, continuous refresh, the batch mode, full refresh, and also incremental refresh. Let's look at the cost curve on the right side. Yeah, the continuous mode, which is using Flink streaming mode, it can provide second level real-time data freshness. But the cost were not reduced significantly, even if we set the data freshness to our level. This is because streaming mode requires resident computing resources. And for the batch mode for refresh, it is the most cost-effective solution for data ranging from hours to days. And for those types of one-time computation, it is the best solution. But when we use full refresh to achieve minute-level freshness, it will be very costly because the full fresh mode will recalculating all data for each time. And the incremental mode, the fresh, it falls between the two, and it can reduce the cost by just calculating the incremental changes only. So, materialized table just complete the last piece of the puzzle for Flink's streaming batch unification, but this is not the end. We will advance the joint optimization for both computation and the storage layer. For the computation part, we will improve operator efficiency, which involves the new disaggregated state, and also offer more computation mode, and enable materialized data sharing. And for the integration of storage, we will leverage the new capabilities of the streaming storage, just do some more computation, offloading, and also together with the new unified stream lake storage, we will aim to provide users a seamless switching from the second level, minute level to hour level operations. Yeah, this concludes the content of stream batch unification. Thank you all. Now let's hand the stage over to Xintong.
Okay, thank you, Lincoln, and thank you, Yuan, for the sharing. So next, let's talk about the streaming lakehouse. Okay, the streaming lakehouse is a new architecture as already introduced in Lincoln and Feng's sharing. It's a new it's a new data analytic architecture that we built with Flink and Paimon. And in this architecture is completely stream batch unified, and all the data in the streaming lakehouse are real-time and curable. But in order for this new architecture to well landed in production, it requires a deep integration between the two projects, Flink and Paimon. So we have been doing a lot in that direction. We have been improving the integration of Flink and Paimon in many commonly used scenarios. For example, in the white table scenarios, well, usually when people want to build a white table, they will use join operations. But join is kind of an expensive operation in data processing. So now with Flink and Paimon, in some use cases where the primary key is available, we can actually replace the join operations with Paimon partial update features. That will significantly reduce the computational cost. And also in some scenarios where we use Paimon as a dimensional table, we have also improved a lot made a lot of enhancement in that direction. For example, we have improved the performance of Flink's lookup join with respect to the data distribution inside Paimon. And also, in order to handle the single key data screw problem, we have supported the Flink screw join optimization. And there's a new feature called processing time temporal join in Flink. This can be used in some use cases to replace the lookup join, especially in the use cases where the dimensional table is not frequently updated, and it also can reduce the computational cost. Well, we are also supporting some new emerging stream batch unification scenarios, such as data synchronization with Flink CDC and the materialized table, which Lincoln just introduced. And speaking for the engine capability, we have significantly improved the performance of reading data from and writing data into Pymon with Flink. For example, we have supported Pymon's delete vector and the data ordering, and also some native file I/O implementations. And for maintenance, now that all the Pymon maintenance actions, for example, the compactions and the metadata cleanups, they can now be easily do with Flink SQL with the procedures, and the named arguments are fully supported. And also for the semi-structured data, which like the JSON or XML, those data are frequently, we see a lot in the AI and feature engineering scenarios. Well, we are also working on some techniques, for example, the variant data types to speed up the read, write, and processing of the semi-structured data. Now that's for the Flink and Pymon integration. Well, the next topic, let's talk about AI. Well, this is actually through our interaction with the Flink community, with the developers and users. This is actually a very frequently asked question. So people will say that it's the generative AI, the large language model are so popular these days. So what can Flink do in this area? Well, let's look at this. This is a simplified version of the RAG architecture. And we know that the idea of RAG is to leverage some kind of knowledge base. For example, some internal data of an enterprise, or maybe some domain-specific knowledges. So RAG leverages such a knowledge base to assist large language model for content generation. Well, in this architecture, there's 2 steps. The first step is to prepare the knowledge base, and we use large language model to generate a vector for each piece of the data in the knowledge base. This is called the embedding. And with the generated vectors are stored in a vector DB. And in the second step, when the user query has arrived, we do the same embedding for this query to generate a vector, and we use that vector to search in the vector DB for the most related contents. And that is, and then we provide the query and the context together to the large language model for the content generation. Well, the question is, how can Flink help in this architecture? Well, we know that Flink is good at real-time data processing. So the question can be asked differently. It's like, is there any demand for the real-time data processing in this architecture? Well, I think the answer is yes. So firstly, the knowledge base is not static. It's keep being updated. So when we do an update to the knowledge base, we expect the result is reflected to in the generated content as soon as possible, and that requires depends on the real timeness of the blue pipeline in this figure. And also when user submitted a query, it is expected that the content will be generated as soon as possible. Well, this highly depends on the performance of the model itself, but the real timeness of the purple data pipeline also matters. And we observed that in this architecture, there's a critical path. That is the invocation of the large language model for both embedding and content generation. And in order to speed up this critical path, the Flink community has introduced the ML model invocation support in Flink SQL. So now Flink users can just use Flink SQL to create a model, just like creating a catalog. So we can define the input and output data structures of the model, as well as some model-specific arguments. And after defining this model, we can just use this model. We can invoke it inside your Flink SQL, just like using a function or table functions. Well, this will help integrate the model invocation together with the data processing and the validations before and after the model invocations. And this feature the design has already been approved in the Flink community, and it's currently under developing. And this is the first step that the Flink community take towards the generative AI area, and we believe that there will be more efforts towards this direction. So this is what we bring you today for the Flink 2.0, and thank you for listening.
Thank you, Mr. Xintong Song, together with Mrs. Yuan Mei and also Mr. Lincoln Lee for introducing us to the new version and what's new in Apache Flink 2.0.